All right, so welcome everyone to the second day of Dynamic Algorithm Workshop. And today we will have a terrific set of people to give tutorial talk about a bunch of things again. And the first talk is going to be about dynamic matching. And in particular, the powerful technique in this area is dynamic sparsifier. Our first speaker is David Wajc. He is now at Stanford and will soon join Technion as an assistant professor. So David Wajc, take it away.
Thanks, Thachapol and Sam, for the invitation to speak in this terrific workshop. So far, there's been a lot of really exciting stuff to hear about, some cool open questions and a good overview of some ideas. And in my attempt to contribute to this today, as Thachapol said, I'm going to try and tell you a little bit about the kind of recent developments in dynamic matching and their connection to one kind of key connecting theme, which is sparsification. All right, so with that, let me just at least start off and make sure that we're all on the same page. I guess everyone here probably knows what the computational model is, but just to start us easy, because this is still a bit early in the morning. So what's the computational model we're looking at? We're looking at dynamic algorithms, specifically dynamic graph algorithms, where our input is an n-node graph undergoing edge updates, so additions and deletions. So the animation here, you have some edges added and removed over time, and you want to kind of react to this one way or another. In particular, in this talk, we're going to want to react by maintaining a matching M. So this set of red edges, for example. So a set of vertex disjoint edges of small approximation ratio, and we'd like to do so quickly. So the approximation ratio, as usual, will just be, we're comparing against the optimum matching at every point in time. We'd like this ratio to be small. So for example, here, this red matching is 3/2 approximation at this point in time. So whatever algorithm gave me this, if it's a deterministic, is at least 3/2 approximate. Okay, might be worse on some inputs. Okay, and now let's focus on this point of quickly. So if you think about this for not too long, so the kind of standard naive algorithms are, well, okay, this is a polytime computable problem, just recompute from scratch at every point in time, but I don't have to tell anyone here that this is wasteful. If you think about it a little bit more, about a ton more, then you'll come up with some simple maximal matching, inclusion-wise maximal matching, which will give you a 2 approximate solution. It's fairly easy to implement in order max degree time or order n time. And so really the question kind of in this area is, this following flavor: what's the best approximation you can get in, say, linear in n time? Can you do better than 2? What's the best you can do in sublinear in n time? Same type of question. What's the best you can do in even polylog or maybe even constant update time? All right. So as it turns out, you can do better than these 2 naive algorithms, and there's been a little bit of work on this over the years. I'm not going to read through any of this, of course, but just to kind of give you a sense of the wealth and breadth of work here. So pretty much all your favorite authors and all your favorite venues. Let me maybe point out one thing. I guess I kind of started off by implicitly assuming we need an approximation. And if you look at the all these works marked in red, and I apologize if I'm missing out on some others, all of these works show that there's some hardness associated with this problem, and in particular under standard computational, under standard fine-grained assumptions. Strong exponential time hypothesis in the bottom right here is a typo. This should be, say, orthogonal, online matrix vector conjecture. This problem requires essentially linear time if you want to solve it exactly. Okay, so all I'm trying to tell you with this quick animation is that we do indeed need to somehow settle for approximation if we actually want fast algorithms. All right, all on board? All right, good. So here's the rough landscape. So Simon showed something similar yesterday. I'll do the same with just a few more references. So just to kind of be clear that we're all on the same page, the y-axis is update time in log scale. So lower is better, of course, and the x-axis is approximation ratio. So further to the left is better. I'll start off with the hardness result I mentioned. So this bar here really should be kind of a line, but no one would see that. So what we have here is that if you want a 1 approximation, it seems that lower than n is impossible. Okay. On the other hand, if you kind of squint at this enough and ignore epsilons, then we can get exactly that. We can get a 1 plus epsilon in linear and n time. Good. If you want faster algorithms, then you can do quadratically faster and get root n time, but now you have to pay in the approximation ratio and get something like a 3/2 approximation. And finally, if you want blazingly fast algorithms, you want something exponentially faster, then you have to go all the way to 2 approximation. And there's been a lot of work, particularly in that bottom right quadrant. Finally, I'll also point out there's a number of trade-offs achievable in this kind of somewhere between 3/2 and 2. Probably most of them a little closer to 2. Okay, so you can trade off approximation ratio and get something say a little better than 2, and polynomial time, but much better than root n. Perfect. Any questions at this point? Just kind of reviewing what's known. Okay, so the plan for this talk is to talk about one common theme to essentially all of these results, barring a few here and there, which is that of sparsification. And I'll give you a number of example sparsifiers, kind of pointing out these, what's going on behind the scenes in these 3 main regimes. I'll show you 1 plus epsilon approximation, approximate sparsifier, 2 plus epsilon approximate sparsifier. There's a reason why this is going to be out of order, and 3/2 plus epsilon approximate sparsifier. Okay, finally, I'll conclude and reiterate some open questions from yesterday and maybe some other stuff. Okay, some guest appearances by kind of classical characters in the matching theory world. Fractional matchings, vertex covers, and edge colorings will pop up either implicitly or explicitly. All right, so let's start with this notion of sparsification. So the general technique is, maintain some kind of sparse subgraph that will serve as a good representative of the whole graph. Okay, so in the context of matchings, we want some sparse graph that still contains a large matching. Okay, the kind of intuition here is that, instead of working on the entire graph, this is smaller. We're, used to thinking that our runtime is dependent on the size of the input, so that naturally should help. Okay. So the illustration the figure you should have in mind is you have your input graph, you throw away some edges, and hopefully what's left still contains a large matching. So what we have here, max matching on the left is 3, and the max matching of the sparsifier is 2. So it's a 3/2 approximate sparsifier. All right. So let me try and kind of motivate where sparsifiers, why sparsifiers are useful for matching. And let's start with one key observation made by Gupta and Peng in Fox almost 10 years ago. And the observation is a fairly simple one. It says that if you have in your hand an alpha approximate matching at a particular point in time, and then for a small number of steps, you do basically nothing. Okay, just kick back and relax. Okay, it's been a long day, do nothing. Okay, then what you have in your hand is still essentially an alpha approximate matching. Okay, kind of intuition being, the max matching didn't change by too much, neither did yours. And if you want to kind of convince yourself that the math actually works out, so here's our example from earlier. We had a 3/2 approximation ratio. We've now made epsilon m updates, so the red matching has maybe decreased by epsilon m edges, so 1 minus epsilon multiplicative factor. The purple matching has increased by at most epsilon m edges. Since m is a matching, it's no greater than opt. So the purple matching has increased by at most epsilon opt edges, or 1 plus epsilon multiplicative factor. And so the 3/2 becomes, well, still basically 3/2, right? So the numerator increased by 1 plus epsilon factor, denominator decreased by 1 minus epsilon. We're still basically where we were a minute ago. Okay, so here's a kind of a very simple algorithm that comes out of this immediately, which is blazingly fast for bounded degree graphs. So here I'll use the notation, the standard notation. M is a number of edges, delta is max degree. And here's the observation, or the kind of algorithm that pops out of the observation on the previous slide. Just run your favorite static 1 plus epsilon approximate matching algorithm. Okay, it's a bunch of near linear time algorithms for this. So my personal favorite is Dwan and Petty, but your mileage may vary. That also works for weighted matching, so I guess that's maybe why I like this better. And then what you do is you take this matching and just, again, do nothing for epsilon m steps. Okay, the analysis is fairly direct from what we said in the previous slides. We were 1 plus epsilon at a certain point in time, and a few steps later will be 1 plus order epsilon. Good. How about the amortized update time? And just for folks here who don't always work on dynamic algorithms or haven't thought about this for a while, quick recap. Amortized update time f of n means that for any update sequence of t updates starting from an empty graph, we take at most t times f of n steps. Okay, this should be contrasted with worst case update time, where with a stronger notion of a worst case update time, where every update takes f of n. Okay, so what's the amortized update time here? We're spending m work every roughly opt steps. Okay, so that's something. At least at first look, this doesn't. First glance, this doesn't look great, right? Like the graph could be very dense, opt could be tiny. Well, it turns out that there's a limit to how large the gap between these two could be, and in particular, these two can at most differ by a factor of max degree. And if you've never seen this before, there's a fairly simple argument that says that in every graph, the number of edges is at most twice the max matching size times delta. Basically, just look at the endpoints of your favorite max matching. This is a vertex cover. And so this covers all the edges. There's most delta of these per vertex. Okay, if you follow that, that's great. It's not particularly important. The kind of key takeaway here is that if you have a bounded degree graph, you can maintain large matchings in it. Basically 1 plus epsilon approximate matchings in the degree time. Okay, so what does this suggest? This suggests kind of a natural next step. Let's not work with the entire graph in case the max degree is actually large, but instead just maintain a subgraph that contains a large matching and has bounded degree, and we'll be able to maintain exactly the max matching in that thing, which would be a good approximation of the overall. Okay, so let me maybe add some slides on top of what I just said right now. So here's a general framework. Step one, or maybe not really step one, kind of in the background, maintain an alpha approximate matching sparsifier. So a subgraph that contains a matching that's an alpha approximate to the overall matching, max matching. Guarantee that this has max degree delta, and do this in update time t. Periodically compute a 1 plus epsilon approximate matching in this subgraph. This will be linear in the size of this subgraph. So this will be at most of size opt times the max degree of that subgraph. And then again, for epsilon m steps, do nothing. Okay, that's it. Okay, so the analysis is essentially exactly what we saw before. At the beginning of every one of these phases, you have roughly alpha approximate matching. After a short phase, nothing really changed. You're still alpha approximate. And the runtime is the max degree of the sparsifier plus the time needed to maintain the sparsifier. Okay, fairly direct. Let me point out that, okay, so really what's going on here, there's some kind of equivalence between the two. I'll show you that there's a lot of places where this crops up in the literature, and well, okay, I kind of pointed out one direction here, right? So if you have an alpha approximate max degree delta update time t sparsifier, then this gives you essentially as good an approximation, actually a matching in time that's t plus delta. And kind of the opposite direction is fairly trivial, right? If the max degree here is less than t, then I mean this is equivalent to maintaining a matching essentially, right? I mean the matching itself is the sparsifier you want. So the reason you're wondering, oh, is this really the right way to look at this? Well, yeah, this is like the only way to look at this essentially. It's kind of the one takeaway to take from this talk. Okay, good. So sorry. Hopefully, any questions at this point? Good. Good. So hopefully at this point I've convinced you that sparsifiers are the best thing since sliced bread. And now we're going to look at a bunch of examples and see what kind of results we get. So first we'll see some local sparsifiers that give you 1 plus epsilon approximation. Then we'll talk about kernels that will give you a roughly 2 approximation. And then we'll talk about something kind of in between, which is called edge degree constrained subgraphs. And the reason I'm going out of order is to maybe motivate the last one, which is maybe a little less intuitive. Okay, so I'm going to spend one quick slide just to give you a sense of results that would give you 1 plus epsilon approximation. So there's a number of different ways of getting this, but possibly the most elegant and most general, this is maybe something for you to take from this talk, even if you don't work on dynamic algorithms, but you do care about approximate matchings, is the following, maybe not well known enough result of Solomon's, which says that, sorry, let me go one step back. By essentially locally making changes to your graph, you can maintain a sparsifier of bounded degree, which still contains a 1 plus epsilon approximate matching. And I'm going to state this result in terms of the number of edges of the graph, but you can actually refine this in terms of the arboricity of the graph. So if you like think about arboricity, Eva's nodding her head vigorously, then this is you might find this useful. Okay, so here's the statement. Suppose every edge marks some root m over epsilon of its edges. Okay, however the hell you want. And we look at the subgraph that is marked by both of its endpoints. Then the claim, which I'm not going to prove here, is that this contains a 1 plus epsilon approximate matching with respect to m. Okay, and I pointed out that this might be useful in a number of other computational models. This is very local. You could think of doing this in a distributed setting and a bunch of other settings. And so I had some animation for that. But look up Shai's paper to find some example applications of this, as well as follow-up papers for more applications. Okay, so I'm not going to prove this, but let me kind of go through kind of the template that we're going to see in this talk with this illustrative example. So what's the degree of this sparsifier? Trivially, it's at most root m over epsilon. No edge has more than the number of edges it marked in the sparsifier. The update time is, trivially, you can do this in constant time. There's really nothing fancy going on here. And what you get from this, if you plug this into the framework from a few slides ago, is that there exists a deterministic 1 plus epsilon approximate matching algorithm in root m update time. And I guess the table I showed you earlier, I was talking about dependence on n. Of course, root m is never more than n. Questions about this quick slide? All right, let's move. All right, so now let's talk about a different sparsifier, which cropped up in that very busy bottom right quadrant in the table I showed you earlier, in the plot. Sorry. So a kernel introduced by Bhattacharya, Hensiger, and Italiano in 15 is the following subgraph. We say a subgraph H is a B epsilon kernel of G if the following two properties of the degrees in H are satisfied. So first of all, we wanted to have bounded degree. In particular, the max degree is at most B. And on the other hand, for every edge we decided not to take into the matching, into this kernel, into the subgraph, we want that at least one of its endpoints essentially has this constraint tight, okay, up to some slack parameter. Okay, so that's what's written here in a bit, maybe too much notation, right? Every edge in the graph, but not in the kernel, has one endpoint of degree almost B. Okay, let me give you a quick example of this for B equals 3 and epsilon equals 0. So here we have a graph with max matching, which is just the horizontal edges. And what we'll end up taking is all these green edges. So every node has at most 3 edges. And every edge we didn't take, so in particular all the horizontal edges, has at least 3 incident has at least one endpoint with at least 3 incident green edges. Okay, and you'll notice that this sparsifier has max matching 3, okay, whereas the overall graph has max matching 6. Sorry, so if you don't see this, the sparsifier only connects 6 nodes, right? It's not going to match more than 3 edges. Good. So this sparsifier on this example is a 2 approximate matching sparsifier. And what I'm going to convince you of, maybe very briefly, is that this is actually the worst example up to epsilons. So the rough intuition is that this is, it's not the rough intuition. What this is essentially an approximate maximal B matching, right? We're allowing to match each node at most B times. And if we don't take a particular edge, it's because one endpoint at least has basically B edges. And here's the theorem we proved with Arar, Chechik, Cohen, and Stein in 2018. What we showed is that any B epsilon kernel is essentially a 2 approximate matching sparsifier. So there's a bunch of notation here, but take B to be at least 1 over epsilon. What this is saying is it's a 2 plus epsilon matching sparsifier. Let's see, do I have a short proof of this? Yes. Okay, so I'm going to give you like 2 quick lines just to give you a flavor of this. This is not going to be a real proof by any stretch of the imagination, just to give you a flavor of how you might prove this. So step 1, we show that this kernel contains some large fractional matching in terms of the max matching. Okay, so we match edges to some fractional extent, and no node is matched to an extent of more than 1. For bipartite graphs, that means we're done because the integrality gap of the fractional bipartite matching polytope is 1. So if you have a fractional matching of value x, you have an integral matching of value at least ceiling of x. Okay, for general graphs, little use of Vissing's theorem. Some edge coloring magic shows you that you're basically losing nothing, and there's still a large integral matching in this thing. And that's where this +1/b funky term crops up. Okay. If you follow this proof, great. If not, it doesn't really matter. What are we going to do with this thing? So again, we want to plug this into our framework for fast dynamic matching algorithms. So we need to figure out what the update time is and what the max degree is. Okay, so max degree is fairly easy, right? Like first constraint number one of these subgraphs is that they have at most b edges. And so the question is, how fast can we maintain these kernels? And okay, spoiler alert, we'll be able to do this in polylog time, or even constant time in some regimes. And I'll try and give you a sense of kind of how you get these fast kernel maintenance algorithms. And in a nutshell, again, fractional matchings make an appearance. So there's a number of dynamic fractional matching algorithms, all due to Cyan and co-authors, that allow us to maintain a fractional counterpart to kernels. And so really the question is, how do we round this into an integral kernel? Okay, and there's I guess three approaches for this to date. Hopefully I didn't miss any of the references. So there was first approach for this was by us in iCalc18. We gave a randomized algorithm versus an oblivious adversary. Then subsequent work in STOC'22, I showed how to do this versus an adaptive adversary, still randomized though. And subsequently, Cyan and Peter, and then Peter showed how to do this deterministically, first with amortized update time and then worst case. And I've got a small asterisk on these latter results because it's not quite kernels, but kind of morally we're doing the same. We're talking about the same thing. Good, so I'll tell you kind of what results crop out of this, but I think this point about oblivious and adaptive cannot be overstated. So I think I'll spend maybe one quick slide just to remind people, or maybe tell people who weren't in the session yesterday what this distinction is and how careful you should be when using dynamic algorithms to speed up your static algorithms. Okay, so a quick digression. We're going to talk about types of adversaries, oblivious versus adaptive. So in the dynamic algorithms literature, we distinguish between two types of adversaries, or two types of sequence generating, update sequence generating mechanisms. The first is the oblivious adversary, which looks kind of simple and cartoonish. And this determines its update sequence in advance based on the algorithm's pseudocode, but not on the algorithm's performance so far, and in particular, not based on the algorithm's randomness. In contrast, there's a much more refined and much more intimidating looking adaptive adversary, which determines its algorithm, its update sequence in an adaptive fashion based on the algorithm's execution so far. Okay. And again, I'll reiterate this point from yesterday. I won't go into this in too much detail, but you're welcome to ask me more about this later. Being able to deal with adaptive adversaries is crucial if you want to be able to use this algorithm in an adaptive fashion. Sorry, as a black box. Okay, so think of some kind of outer loop that, based on what your dynamic algorithm is doing, decides what the next sequence is. And, this crops up in a bunch of algorithmic paradigms: interior point method, multiplicative weight updates, et cetera, and I'm sure you can think of more. So really, what we want is to kind of deal with this dodgy-looking character. And I'll point out that this has been kind of the underlying motivation for a lot of work on deterministic algorithms, because deterministic algorithms naturally work for every update sequence, in particular for one that depends on what you've done so far. If you want to hear more about this, then there's at least one talk about this. Touchable, I want to say Friday. Is that right? Okay, so there's one really great work about talk about this on Friday. So I cannot recommend this enough. So go see that. Okay, back to our regular program. So again, what are the fast matching algorithms we get via rounding? So there's a number of algorithms for maintaining dynamic fractional matching algorithms. So step number one is round these one way or another, obtain a kernel or something similar to it. And then from the arguments we said earlier, assuming this first step is fast, then what we get is a fast dynamic matching algorithm. Okay, so I won't kind of reiterate the points here. Let me just tell you what are the kind of results that we know how to show versus adaptive adversaries in this regime. So what we can do using this general template is maintain a 2 + epsilon approximate matching in the following update times. So we can do constant amortized time with a randomized algorithm that works against adaptive adversaries. And we can also do polylog time, worst case deterministic. It looks troubled, so maybe I'm misquoting something here, but this is roughly the state of the art. All right, any questions at this point? Going once, going twice. Okay, good. So now let's switch gears and talk about kind of the intermediate approximation regime, the 3/2 approximation. Let's see, we started that. Okay, we're good. Good. So a quick recap of what kernels were and what the tight example was, and this will kind of motivate this edge degree constraint subgraph, which I think at first look maybe feels a little unintuitive. Okay, so again, we wanted a graph of max degree B, and for every edge that we decide to not include in the subgraph, one of its endpoints should have degree roughly B. Okay, so here's our tight example. And notice that, I mean, why are we getting a 2 approximation here is because every edge of opt has, one endpoint that has some edges and the other one, well, has 0 chances of getting matched, right? This is really like the extreme case. So really what we'd like to do is to give the other endpoint some chance of being matched. And in particular, we'd like to give it some number of edges. So what we're going to do is ask not for one of the endpoints to have a high degree, we're going to ask for maybe the sum of these endpoints degrees to be high. Okay, so notice, okay, let's walk around a little bit, right? So all these green edges have edge degree, okay, so some of the degrees of their endpoints be 2B in the sparsifier, and all the opt edges have their edge degree be 1. So let's actually balance that term rather than degrees. Okay, and the intuition again being that now this gives opt edges, both of the endpoints at least some non-negligible chance of being matched. Okay, right, so that was the point here. So ideally, we want to include a lot of these optimum edges. So in this drawing, we want to include a lot of these horizontal edges, or we want to have both of these endpoints have many edges along which they can match, and then intuitively you should be doing fine. Okay, so this brings in this new definition of Bernstein and Stein from 15. I'm crediting both works, but first, of course, define it. So we say a subgraph H is a B epsilon edge degree constrained subgraph, or EDCS for short, if it satisfies the following. So for every edge UV, the sum of its endpoints degree is at most B. So again, this is going to guarantee a bounded max degree, so that we already are clear that this is useful for dynamic implementations. And in addition, for every edge UV in the graph, which is not in the sparsifier, the sum of degrees is basically B. It's at least B times 1 minus x. And if you think about the example from earlier, well, this will include all the horizontal edges, right? The horizontal edge. So how do you see this? Maybe I should add an animation here. But the horizontal edges we'll see maybe. Okay, let's say we start with some value on the middle edges. On average they'll get to some value of say like B over 2 because the sum of degrees cannot be more than B. And so the external edges have, one endpoint with degree B over 2, the other with 0. So we need to take these horizontal edges. Okay, so those of you who managed to remember the drawing, maybe I could have gone a little bit back. Okay, so what I'm saying is all of these green edges have their the sum of their degrees be B. So kind of on average, the nodes on the right that have these green edges and the nodes on the left that have green edges have degree B over 2. So these horizontal edges should actually be added, or at least the vast majority of them. Okay, so this addresses this kind of bad example. Let me kind of point out the bad example for B epsilon edge degree constraint subgraph. So this drawing is a little busier. So what we have here is an extension of the thing, the example from the previous graph. Again, the max matching is the horizontal edges. And I guess with this animation, it's maybe not super clear, but these 3 horizontal edges in the middle are missing. Okay, so B, basically what we have here is this kind of the horizontal edges are bicliques of degree roughly B over 2. And so these horizontal edges see that the sum of degrees of their endpoints is B, so we don't need to add them. And the fact that we don't add them kind of screws us out of a third of the matching size. Okay, so what we have here is a 3/2 approximate sparsifier for this particular example. And the following theorem states that this is the worst example. Okay, so this was proved in a lot of works in the literature. I didn't try to be exhaustive here. But broadly, the state of the art is that if B is at least some multiple of 1 over epsilon, then a B epsilon EDCS contains a roughly 3/2 approximate matching sparsifier. Okay, and again, I'm going to give you maybe 2 quick lines just to kind of tell you about some cool proofs there, but really not tell you anything at all. So I think my favorite proof of this is by Asadi and Bernstein and Sosa 19. If you're looking for a sleek paper to teach in some grad course or something, then I'd recommend this one. So for bipartite graphs, you rely on the extended Hall's theorem to show that bipartite graphs, EDCSs are 3/2 approximate sparsifier. And then kind of the really sleek idea here is for general graphs, you kind of reduce to the bipartite case by considering some natural bipartition. So all the edges of opt you flip independently, and all the other nodes you put either on the left or on the right independently. And then maybe Chernoff or Lova's local lemma will show you that there's a subgraph of this EDCS, which is an EDCS of the obtained bipartite subgraph, which has a max matching size of the same value. Okay, if you follow that, that's great. This is kind of a, no, too fast. All right, I'll explain this afterwards, but just this kind of flash that there's some nice idea going on here, and this is maybe not quite the point of what's going on here. Anyway, really sleek proof here. Sorry, I won't do this in 30 seconds. Okay, so I'll point out before telling you about the implications for dynamic matching that this has implications in a number of computational models. And those of you who were looking at the program a few weeks back will notice that my slot was supposed to be used by Aaron to tell you about how cool EDCS is and not just dynamic algorithms. Unfortunately, Aaron couldn't be here, so I'll just tell you about the implications for dynamic algorithms. But you know, look up some of these references to find some really cool applications of this matching sparsifier. All right, cool. So what do we get out of this? So first of all, a theorem that's been proven in increasing level of generality in the last few years is that you can maintain a 4th root of m epsilon EDCS in time 4th root of m. Okay, so what does this give us? So this gives us a sparsifier of low max degree, 4th root of m, right? That was one of the first properties of the edge degree constraint subgraph. And we can maintain this sparsifier in 4th root of n time. Okay, so all in all, what we get from these works is that there exists a 3/2 plus epsilon approximate 4th root of m update time algorithm. I guess at this point, we also know how to do this deterministically and without this hat over the. All right. Okay, this is last technical slide. Let me just maybe summarize kind of what's the main takeaway here. So for dynamic matching literature, sparsifiers have played a crucial role, and this is really not surprising in any way if you think about it, because essentially dynamic matching sparsifiers are equivalent to dynamic matching algorithms. Okay, so there have been many results that follow from this connection, and I give you a little bit of a flavor of some of them. A quick recap of the state of affairs if you're kind of wondering where you could insert yourself into the long list of references. So again, on the hardness front, one approximation seems to require n update time. We can essentially match the same thing if we're willing to do 1 plus epsilon approximation. You can do quadratically faster if you are okay with the 3/2 approximation. And finally, we can do exponentially faster if we're okay with getting like roughly a 2 approximation. And in addition, there's some trade-offs in between. Okay, so let me conclude with maybe kind of the 3, in my mind, most obvious open questions here. We talked about the present, let's talk about the future. So question number 1, on the hardness side, we really only know how to say something at on the y-axis. Okay, we know nothing about approximation, about hardness of approximation here. So maybe reiterating some of the questions that came up in the panel yesterday, can we show any kind of hardness for approximate dynamic matching? Okay, unconditional is maybe a little too early for us. Just give some kind of conditional hardness based on strong exponential time hypothesis or your favorite hypothesis. Maybe just make sure the hypothesis is not dynamic matching 1 plus epsilon is hard. That would be a little uninteresting. Okay, on the approximation, on the, well, I guess algorithmic front, you could ask for better little order of n time algorithms. So at the moment, we're stuck at basically 3/2 plus epsilon is the best approximation we know in sublinear and n time. So can we do better? Can we hope to get even 1 plus epsilon? Okay, so again, as I said, we have like no hardness whatsoever. As far as we know, 1 plus epsilon could be constant time. Okay? We're so far from that, but okay. And finally, closer to the x-axis, what's the best constant or polylog approximation ratio we could get. Okay, and in particular, can we break 2? Right, we have. I guess we're already in double figures, double digits for 2 or 2 plus epsilon approximation. Can we finally move even a smidge to the left? And I won't keep you in suspense. The answer is yes. So as Sayan announced yesterday, together with Sayan, Peter, and Thachapol, we have a 2 minus constant approximate dynamic matching algorithm in polylog update time. Okay, so that's maybe not so much an open question. Of course, there's a question of refining these bounds and strengthening them in a bunch of various ways. But just to kind of give you a sense of the excitement of moving forward, what more we could hope to do. All right, so I think that's more or less my time. I'm happy to take any questions you may have. So EDCSs have been useful in streaming so far, I guess, in multi-pass regime or random order. Yeah, but I mean, obviously for streaming, the open question is B2 in single pass, and there unfortunately they have not proved to be the key ingredient. But maybe they will. I don't know. Yeah, a little bit. Nothing so far. Nothing to report. Sure. Daniel. The hardness is based on the online matrix vector conjecture. So for those who don't know it, you get a matrix, you get row after row after row. You want to multiply these, but you don't know the next one coming up, right? If you knew ththem all in one go, these are n vectors. If you knew them up front, this is just matrix multiplication, right? You could do this in subquadratic time. The conjecture is that if I reveal these rows one by one by one by one, this is going to take you cubic time. The hardness is even in planar graphs, even in an incremental setting, even if you only care about the value of the max matching. What else? Even if you know the update sequence, so that's really crazy, right? Like this is not even really a dynamic hardness problem. It's an offline problem, an offline hardness. Yeah. All right. Other questions? All right. Thanks for your time.